Welcome to Einstein's Mechanics. In today's episode, we are going to tackle series parallel circuit. So in this episode, we are going to talk about a circuit that has both series and parallel resistors all together. So how do we make the analysis? So we can look at a diagram in the form of a series and a parallel circuit. So we have this circuit this way. We have our resistor, and there's a resistor here too. Now we have our resistor 3, and this is our diagram. So I'll call this R1 and I'll call this R2, and this is my R3. This is my voltage source and there's a current going. So looking at this diagram, now we have 3 resistors, which some of them are in series and some are in what? Parallel. So how do we tackle a whole system like this? That's what we call the series parallel circuit. You can find series resistors and you can find parallel resistors in the same circuit. So in situations like this, we are going to use what we call the network reduction. Network reduction. What it means is this whole figure or this whole diagram, we are going to reduce it to a single and a simple diagram. Are you okay? So we are going to reduce it such that at the end of our diagram, we are going to have all the resistors being represented by one equivalent resistor of the same resistance. That is going to produce the same effect as this arrangement. So first, you have to check that looking at the diagram now, if they are parallel resistors, you have to convert them and solve them as one. So this part, we have 2 parallel resistors. We can now combine them and solve them. Then the answer we get is going to be in series with this third resistor. Then after also solving, you're going to get the final answer for equivalent resistance. Now let's get to work and reduce this system. If I want to reduce this system, first I will solve these 2 parallel resistors. They are parallel because when the current gets here, one is going to move here, I2, and there will be I3. This I1 is coming here, and this will be the same as I1. So these are parallel resistors. So I'm going to solve them. That resistor 1 is parallel to resistor 2. So after using the formula to find the equivalent resistance, your diagram is going to be in this form. So your diagram can be reduced to, now these 2 resistors has been combined to a single equivalent resistor. Now resistor 3 is also this way, and this is my diagram. So this is resistor 1 being parallel to resistor 2, and this is also resistor 3. What can you see now? You can also see that resistor 1 and 2, which are parallel to each other, reduced to a single resistor, is now in series with resistor 3. So we can also find the equivalent resistance as RQ being equal to, we know how to find the resistance if they are in series. That's resistor 3 plus resistor 1 parallel to resistor 2. And this is going to give us equivalent resistance. So now the diagram can be reduced to this form as a single resistor this way. So whatever we get for the answer here is going to be the total resistance offered by these 3 resistors. Are you okay? So this is what we call the network reduction. You are going to focus on 2 or more resistors at an instant and combine them gradually until you find the final equivalent resistance. Let's look at another diagram if we can reduce it. Let's look at this. So let's call figure 2. If we have, this is our diagram, resistor. We have one resistor also here. And this is our diagram. So what can we do here in order to, let's call this resistor 1 and our resistor 2, resistor 3, and resistor 4. So we have 4 resistors. Some are in series and some are parallel to each other. So here in such cases, how do we find the equivalent resistance? The equivalent resistance. It's very simple. We are going to still use the reduction approach by considering 2 or 3 resistors at a time if they are parallel to each other or they are in series with each other. So when you check resistor 1 and 2, they are in series. When you check resistor 3 and 4, they are also in series to each other. Are we good? Resistor 1 and resistor 3 are parallel. This and this are also parallel resistors. But it will be more simple if we tackle those in series first. So look at this. I want to reduce this. So can I say resistor 1 plus resistor 2? It is going to give us, let's call it resistor prime. And since R3 and R4 are also in series, R3 plus R4 is also going to give me, let's call it R prime prime. So if I'm going to reduce this, now the summation of this is going to give me 1 R prime. The summation of this resistor S is also going to give me this. So if I'm reducing the circuit, this is what I'm going to get. The circuit is going to be in this form. Now here I'm getting 1, and at this part I'm also getting 1, and this is it. So this is now R prime and this is R prime prime. Looking at R prime and R prime prime, they are also parallel to each other because the current I coming here is going to divide into I1 and I2. The same current is not passing through them. So now we know that resistor R prime is parallel to resistor R prime prime, and we know how to solve for the equivalent resistance. So 1 over the equivalent resistance will be equal to 1 over resistor and 1 over resistor prime prime. So with this, we can also get a final answer for the equivalent resistance, and that resistance is going to be the total for the circuit. So finally, I can reduce the circuit this to a circuit of this form. Combining both R prime and R prime prime, I'm going to get, let's call this the equivalent resistance. So R equivalent here, which will give us the same effect as the other. Let's solve an example and see how best we can see that. So example 1. So find the total resistance RT in the circuit. So we have a circuit combining series of what? Resistors, and we have to find the total resistance in this entire circuit. Looking at this, we have resistors. Some of the resistors are in series, others are parallel to each other. So we have to find the total resistance. Now let's write down the parameters. Starting from this, we have our R0 should be equal to 24 ohms. We also have R1 as 60 ohms, R2 100. We have R3 to be equal to 140 ohms, R5 or R4, that is 200. This is R4, 200 ohms. Our R5 is 150 ohms. Now R6, which is equal to 50 ohms. So now, first you have to pay attention to the diagram and identify those resistors in series. First, find those in series and also find those in parallel. So you can see that from here, these two resistors, resistor 1 and resistor 2, are in series connection. And resistor 6 and resistor 5 are also in series connection. So why don't we solve for those in series? Very simple. And we continue with those parallel to each other. So we know that for series connection, so now we are going to consider the series resistors. And we know that if two resistors are in series, is the summation of what? The resistances to get the equivalent resistance. So for resistor 1 and resistor 2, since they are in series, their equivalent resistance is going to be resistor 1, which is 60 plus, resistor 2, 100 ohms, and that is going to give me 160 ohms for resistor 1 and resistor 2. We also know that resistor 5 and resistor 6 are in series, so summation of them. Resistor 5 is 150 ohms and resistor 6 is also 50 ohms, and that is going to give us 200 ohms for those in series. Now that we are done with the series connection, can we redraw our diagram to know how it is being reduced to? Yes, so first I'll draw the diagram again and see how it has now reduced to. This is my first resistor. It is still there. And resistor 1 and 2 are now equivalent with 1. I have my resistor 3. Resistor 5 and 6 is now 1. And I also have resistor 4 over here. Are we okay? This way. This is the equivalent diagram that we have. Those that we've not solved, we will just write them again. Resistor R0, which is 24. Everything is in ohms. And this is going to be our resistor R1 plus R2 because they were in series, and that gave us what? 160 ohms. And this is resistor R3. We know R3 to be 140 ohms. This is also resistor 5 plus resistor 6 over here. We also know that that is 200. And finally, this part is our resistor 4. And we know resistor 4 is also 200 ohms. So now what do we do again? We can also see parallel arrangement. Now we don't have series again, we see parallel arrangement. Can we also say resistor 4, this resistor 4 and resistor 5 plus 6 are also parallel to each other? Yes, they are parallel to each other. So if resistor 4 is parallel to, that's when we have resistor 5 plus resistor 6. They are parallel to each other. Let's call the results as resistor prime. And we know that these two resistors, we are going to have it as R is equal to 1 on resistor 4 plus 1 on resistor 5 plus resistor 6. That is going to give us 1 over resistor 4, that is 200, plus 1 on resistor 5 and 6 is also giving us 200. And when you are finding the equivalent resistance for equal resistors, it's just the number divided by, or the resistance divided by the number of resistors you have. So 200 divided by 2, that is also going to give us 100 ohms. So now the equivalent resistance for this part is also known as 100 ohms. So can we now redraw the diagram again to see how it looks like. Yes. Now the equivalent diagram is going to look like this again. So we still have our R0 in place. We have this resistor, which is R1 plus R2, also in place, and that we are having our resistor 3 in place. And this part is also going to be represented by a single resistor. So we have this. So remember, this is our R0. This is also our R3. And this is now our R prime. This R prime of 100 ohms. For solving this parallel arrangement, we have it here now. Are you okay? So now what do we see again? We see that resistor 3 now is also in series again with R prime. Are you okay? So we can find the equivalent resistance. Let's call that as also R prime prime, which is equal to R3, since they are in series, R prime, and that is going to be R3 is also 140, right? That's 140 ohms plus R prime, we just found it to be 100 ohms. So meaning our R prime prime is going to be 240 ohms. So now we've combined R3 and R prime to get equivalent resistance of 240 ohms. So let's now continue the reduction. We draw the diagrams in such a way that we will see how we can take the next analysis. Are we okay? So we have to draw the diagram again. So this is what I'm going to have for the second diagram or the next diagram. I still have my R0 in place. Remember, I still have this one also in place, which is R1 plus R2. Now, these two resistors has been reduced to a single resistor. So this is my diagram now, and this is now resistor R prime prime. So I have 3 resistors. What can you see? You can see that this resistor is parallel to this resistor. So we are going to use the parallel approach to solve for these two to get one equivalent resistor. So now solving the two, you are going to have as 1 on, I'll call the effect of the 2 as R prime prime prime, which is equal to solving for parallel for 1 on resistor 1 plus R2 plus 1 on resistor prime prime. I'm solving for these two resistors as parallel to each other, and that is going to give me 1 on R prime prime should be equal to 1 on, this is 160 plus R prime prime, we just had it as 240, and this is going to give me R prime 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 to be equal to 96 ohm. Are you okay? So now my final diagram is going to be, because now I've solved these two parallel, the diagram is going to be in this form. I still have the R0, so here this is still the R0. I still have the R0, and combining these two resistance to form a single one, we are going to have it this way. So this is now resistor R prime prime prime, and this is R0. So what do you see? You now see that resistor R0 and R prime 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 are in series connection. So since they are in series, I'll call their effect as the total resistance, and that is going to be R0 plus R prime prime prime, and that is going to be 24 plus 96. And my RT, which is the total resistance, is going to be 120 ohms. Are you okay? So now with the effect of the number of resistors we had in the entire diagram, the total resistance is 120 ohms. This is achieved by doing the reduction approach, considering those in series and solving them, considering those in parallel and solving them. You'll get your final answer. Thank you for watching this episode. Check out for the example 2 in the next episode.